In this lesson, we're going to take a look at a couple example problems and go through the methods of heat transfer. Heat always transfers in one of three ways: conduction, convection, or radiation. Both conduction and convection are going to rely on matter. In conduction, it's heat moving through matter. In convection, it's matter carrying heat. But radiation only depends on electromagnetic waves, which means it doesn't need matter. It can move through space, which is handy for us. So the thing that we have to remember is just because we're going to discuss conduction and convection and radiation separately doesn't mean only one of them can occur. In most situations, at least two, usually three of these things are occurring. Conduction is generally best in solids because it actually involves one particle colliding with another particle. And in liquids and gases, if one particle collides with another particle, that particle can shift position and move away. Convection doesn't happen in solids at all because we actually need the net flow of particles in order to have a convection current form. And then radiation, like I said, this is going to involve electromagnetic waves. So let's get into this. Conduction is probably the simplest one to understand. If you think about a solid made up of atoms and say like metals, the metals are all surrounded by their electrons that are free to shift around and move. If I put this end of the metal into fire or hot liquid, that immediately starts to increase the energy of these particles, which causes them to vibrate a little bit more, which causes the particle over here to vibrate a little bit more, which causes eventually that vibration works its way all the way through this, so we get a net flow of heat this direction. Remember, heat is not energy, or is not matter, it's energy. So the particles aren't flowing, the heat is flowing, the energy is moving. And this equation right here describes the rate at which that heat flows. Now remember, Q is heat. Heat is in form of energy. It's energy transfer due to a temperature difference. And so that's joules. This is over time. So a joule per second is a watt. So we're actually looking at power, the rate at which heat is conducted. And this is equal to K, which is called thermal conductivity. And it depends on the material times the area of the conducting channel, I guess, and then it also depends on the temperatures between them, T1 minus T2, and the length that this thing has to travel, right? So if it's got to go a greater length, it's going to have a slower conduction rate. If it's got a bigger area, then more heat can flow faster. So this K depends on the substance. There's a whole table of thermal conductivities in your book. Here it is in the notes as well. And you can see silver's got a very high thermal conductivity constant, whereas air has a very low thermal conductivity constant. These things down here tend to be considered insulators. They have fairly low thermal conductivity. They impede the flow of energy. Energy does not flow quickly, so they insulate or prevent heat from flowing, whereas thermal conductors allow heat to flow fairly easily. And you'll notice metals are pretty high up on that list. Air being a very, very good insulator. Most of the things that we use to insulate ourselves are just designed to trap air. Like fiberglass insulation in the walls of your house is a bunch of little strands of fiberglass, and what those do is they create little pockets where there's air, and those little pockets of air are actually your insulator. Goose down, same thing. A little feather collects and traps a lot of air, and that's actually the insulation there. Now, an example conduction problem, we have the temperature inside the house is maintained at 20 degrees Celsius. The air temperature outside is minus 10 degrees Celsius. A glass window is 5 millimeters thick and has an area of 1.2 square meters. How much heat is lost through the window each hour? So we have the rate at which heat flows by conduction is given by the thermal conductivity, the area, the difference in temperature, T1 minus T2, on either side of those things, divided by L. In the problem, it told us that K is 0.84, so this is equal to 0.84. The area of the window is 1.2 square meters, 1.2 square meters. Notice that this is in fact in joules per second meter degree Celsius. So we're going to need our length to be in meters. That says 0.5 or 5 millimeters. That is 0.005 meters. First, let's get our temperature difference, I guess. So T1 minus T2. So the heat is flowing from hot to cold, so it's going from 20 to -10. 20 minus a minus 10 is 30 over 0.005. Let's just see what we have there in terms of our units. So we have joules for our constant over seconds times meters times degrees Celsius, and then we multiplied that by square meters in our area, and then we multiplied that by degrees Celsius for our temperature, and then we divided that by 0.005 meters for our length, and you can see this meter and this meter work together to cancel that meter. This degree Celsius cancels that degree Celsius, and we are left with joules per second, which is a watt. Okay, and so if we do this math real quick, 0.84 times 1.2 times 30 divided by 0.005 gets us 6,048. 6,048. That's joules per second. Now the question was how much heat is lost through the window each hour. So there are 3,600 seconds per hour, and we get let's see, 217,728,00. So 21,772,800 joules are lost every hour through that window. Now, this is why we don't actually construct windows out of thin sheets of glass. We construct windows out of 2 thin sheets of glass with an air pocket between them, because then we get this layer of air that is a very, very good insulator. And also, we tend not to have that big of a temperature difference between the inside and outside of a window, because the air on the inside is actually fairly still and it's in direct contact with that glass, and so we get some conduction here, and that actually lowers the temperature of the air right next to your window. So this is not going to be the same temperature as like the air over here, because conduction happens fairly slowly in air. It's a good insulator. Same thing on the outside, unless the wind is blowing and constantly putting new air here, which is fairly constant for us. The air here is going to be slightly warmer because it's up against that warm window. And so we design windows to limit heat flow. Now the next one of these is convection. Convection is heat transfer by net movement of particles. And so convection we're not going to do a lot of math with, but what you can see here is if I just have water, it's got a fairly uniform density. If I start heating it up, that causes these particles to spread out and expand, which causes them to rise because now they are buoyant. That means gravity is going to pull the denser stuff down in to fill up that void, so the cool stuff is now going to be by the heat source, which is going to rise and push up. So you get this convection current that forms. Convection currents form naturally all over the place. They drive currents in the ocean, they drive wind patterns on the globe, they are what's responsible for forming thunderstorms and tornadoes. Convection currents are kind of a big deal. They're also a big deal to you. They're basically how your body transports excess heat from the inside to the outside. So you've got this very, very thin layer of skin, and then there's blood running all throughout your body, and it basically runs up next to your skin so that it can bring the heat from cellular respiration up to your skin, which your skin can then radiate and conduct to the air, and also some convection currents there. So it's actually the movement of heat through the movement of blood that brings the heat to your surface that helps maintain your body temperature homeostasis. So there's actually, your blood is actually forming a convection current as well. That's forced convection because your heart is pumping it around, whereas this is natural convection. This occurs and is allowed to flow naturally. And then we get into radiation. And radiation is kind of complicated because it's electromagnetic waves. And electromagnetic waves consist of vibrating fields, an electric field and a magnetic field, which means they move through space. If we didn't have radiation, the sun could not provide energy to our planet because it's empty space, right? There's no matter there to convect or conduct the heat to us. This is the Stefan-Boltzman equation, and it tells us how quickly something emits thermal energy from radiation, and you'll see it's proportional to the 4th power of temperature. this is absolute temperature. That has to be measured in kelvins. So E is emissivity, and it depends on the substance. If the substance is ideal, what we call a black box radiator, then the emissivity is 1, and it perfectly emits all of its energy. It would also perfectly absorb all energy that hits it. This is the Stefan-Boltzman constant. It's a universal constant, like the gravitational constant's universal. The speed of light is a constant. This is the Stefan-Boltzman constant, and it has a value of 5.67 times 10 to the negative 8th watts per meter squared Kelvin to the 4th. So this one is going to be something that I'll write on the board. I won't expect you to memorize, but we'll use it for our equation. Emissivity ranges between 0 and 1. The darker black something is, the closer to 1 its emissivity tends to be. Shinier substances have emissivities that are fairly low because shiny substances are poor radiators. They're also poor absorbers. So it turns out, right, if everything is emitting radiation, then there's always going to be radiation hitting something. So when a substance gets radiation, it absorbs radiation. Well, it only absorbs what it doesn't reflect. So a shiny surface will reflect away that energy, and not very much of it is absorbed. And so lighter and shinier objects tend to reflect more energy, which is why you tend to wear white in the summertime, and it reflects off the heat. Black surfaces absorb energy and get really, really warm, but they also then emit that energy very, very quickly. So if you were going to have, I don't know, like say a thermos, a lot of these are silver and shiny because that actually limits radiation. The darker the color is, the better it is at emitting that radiation. Now, because a substance is not only gaining energy from radiation coming in, but losing energy, we actually modify the Stefan-Boltzman equation a little bit. So now instead of just having temperature, we have a difference in temperature. Now, be careful, that's T to the 4th minus T to the 4th, which is not the same thing as T minus T to the 4th. Don't do that. So T1 is the object's temperature, T2 is the temperature of the environment. The emissivity will be given to you based on whatever the substance or object is, and remember that's the constant for the Stefan-Boltzman equation. So let's look at an example problem here. It says a radiator dissipates the heat from an engine. You guys have probably all seen radiators, box, got a tube coming into one side, fins here. There's coolant moving through this, so there's actually convection bringing heat from the engine to the radiator. There will be air actually flowing over this, which is going to convect and conduct a bunch of the heat away. We're not taking those parts into consideration in this problem. We're just looking at how much the heat is radiated. This is going to be a fairly dark surface because that will allow it to radiate better. The darker something is, the better it tends to radiate. Remember, good absorbers are good radiators. So this is 150 degrees. The air immediately around it is going to be fairly warm, so I've got it at 100 degrees. We're taking the emissivity to be 0.75, and the surface area of all the fins and junk in that radiator would be 2 square meters. So at what rate is heat radiated to the air? So we have Q over T is equal to E, or not E, that's epsilon, sigma A area T1 to the 4th power minus T2 to the 4th power. And so this is equal to 0.75 times 5.67 times 10 to the negative 8th times, okay, this, remember, is absolute. That says 150 degrees Celsius. We've got to add on to that our 273 so that we're actually in Kelvin. 150 plus 273 is 423, and this is 423 to the 4th power minus 373 also to the 4th power. So 0.75 times 5.67 second E negative 8 times, parenthesis, 423 to the 4th power minus 373 to the 4th power. Close that parenthesis, and we see 538 joules per second, or that's 538 watts. So keep track of your units, make sure you're doing your temperature conversions, make sure you're using absolute temperatures. But the Stefan-Boltzman equation is a fairly straightforward one to use to calculate radiation.